Good morning, everyone. This is Chapter 3 of the course Molecular Physics P3321. This chapter talks about the vibrational spectra of diatomic molecules. Let's see together the content of this chapter. First, we will see some experimental results that give evidence of the vibrational spectra or the vibrational motion of the molecule. After that, in order to understand the vibration of a diatomic molecule, we will start with studying the vibration of a single particle classically. After a single particle, we are going to study the vibration of two particles connected by a spring, also classically. After finishing the classical study, we are going to deal with the vibration of the atoms of the molecule or the two particles of the molecule quantum mechanically, and we are going to find the solutions and the energies of this harmonic oscillator. After that, we're going to determine the transition selection rules which lead to the formation of a certain spectrum. We will compare with experimental results. We will see that harmonicity or harmonic oscillator is not enough to describe our spectrum. We need anharmonicity. I will explain these terms later in the course. To consider anharmonicity for molecular vibrations, we are going to replace the potential energy function used for normal spring with the Morse potential energy function. We are going to use the Morse potential energy function, which better represents a chemical bond. And we're going to see again how this correction affects the vibrational energy levels, how it affects the transition selection rules, and the total shape of the absorption spectrum. We will finish at last with some conclusions and some exercises as usual. In the last chapter, we have explained that the diatomic molecules absorb electromagnetic radiation in the microwave region due to their rotational motion. Now we also observe that diatomic molecules absorb electromagnetic radiations in the infrared region. In this region, or these electromagnetic radiations are absorbed not due to rotational motion, but due to vibrational motion of the molecule. And we're going to prove that throughout the chapter. Throughout the chapter, we are going to see that the vibrational spectrum is not formed of a single line. It's formed of an intense line with high intensity in addition to other lines with much lower intensity. Now, if the apparatus used for spectroscopy has a low resolution and if the layer of molecules is thin, the absorption spectrum takes the form of a wide band. We are unable to see the different lines. We see the sum of these lines which appears as a band. This band is called the fundamental band. On the other hand, if the apparatus used for spectroscopy has a high resolution, we are able to see these different lines and the band is resolved into lines. So in this chapter, we're going to consider for the moment the maximum absorption or the highest intensity of absorption, which corresponds to the characteristic frequency of vibration of the molecule. We'll see that throughout the chapter. This slide here shows the experimental observations for the spectra in the infrared region for the HCl molecule. So we observe certain characteristic wave numbers of the bands observed for sure for HCl molecule. We can see that we have a band or a wave number at 2885. We have another at 5668, at 8300, 10900, and 13900. We can also see that the first one has a very high intensity, while all the others have much lower intensities. So these are just observations. We try to make a link between the observed wave numbers or the experimental wave numbers. So we started by subtracting the different neighbor wave numbers or adjacent wave numbers. We subtracted 1 out of 0 to get this number, 2 from 1 to get this number, 3 from 2 to get this number, 4 from 3 to get this number, 5 from 4 to get this number. This is the same method we have done for rotational spectra. But here, we have found that this difference is not constant as in the case of rotational spectra. This difference decreases slowly. So we thought about finding also the difference between the difference. So what we are going to do is that we are going to subtract this from this, again this from this, again this from this from this, and we're going to find these values. Approximately, the difference of the difference is approximately equal. So based on that, we were able to find an equation for the characteristic wave numbers represented by u bar. This is the wave number. This is the calculated wave number using an empirical formula, equals b. B is a constant. K is an integer which can be 0, 1, 2, 3, etc. C is a constant, and K is also the same integer as before. For HCl, B was found to be equal to 2937.3 centimeter minus 1, and C was found to be equal to 51.6 centimeter minus 1. So let's check if using this empirical formula gives wave numbers or calculate wave numbers close to the experimental values. So using this formula and the values of B and C, we were able to calculate the wave numbers again to check if our guess is true or not. So we were able to calculate the wave numbers again and with values very close to the experimental wave numbers. So we should guess that the experimental wave number should depend on an integer k, it should be a quantum number, and its square. يعني بمعنى آخر نستنتج إنه الانرجي لازم تكون quantized لأنه طلع فيها integer، وهيدي الانرجي ما بتعتمد بس على الانتيجر، بتعتمد على سكوير للانتيجر حتى يطلع معنا سبيكتروم بيشبه هيدا اللي نحن عم نشوفه هلا. So لازم theoretical study تكون متطابقة مع الاكسبيرمنتال study. هلا كيف عرفنا انه بدنا نوصل بس للكي سكوير مش كي كيوب والى اخره؟ لما نحن جربنا اول شيء اول difference طلع variable، تاني difference طلع constant، فاكيد تالت difference اذا انا بعمل رح يطلع 0 approximately 0، فلكن تالت order من الكي هو منه ضروري. اوكي it will be 0 بكل الاحوال. So انا بس رح يهمني first order of k and second order of k. So we have our experimental data, we can fit the graph to find B and C. To understand the vibration of a diatomic molecule, it's very helpful to start with classical mechanics. Let's start with studying the vibration of a single particle. Assume we have a particle of mass m, and this particle is connected to a spring. When this particle is displaced from its equilibrium position, it will be subjected to a force called tension. Let's take a look on the figure aside. This is our particle of mass m. This particle here is at its equilibrium position. What is the equilibrium position? It is the position in which the spring has its natural length L0. So the spring is not contracted nor compressed. If the particle m is displaced from its equilibrium position, let's say that the spring is compressed as in this case, so L is less than L0 and the displacement x is equal to L minus L0, it's equal to delta L, it is negative. In this case, the particle is subjected to a force whose direction is towards the equilibrium position. So this is F. This is the direction of F. Similarly, in the case of elongation of the spring, L is larger than L0, x is equal to L minus L0, it's equal to delta L, is positive, and in this case, the particle is also subjected to a restoring force directed towards the equilibrium position. In both cases, it's directed towards the equilibrium position. That's why it's called a restoring force. يعني بترجعنا محل ما كان equilibrium position أو محل ما الموقع الأساسي تعول البارتيكل. Hooke found that this force F is directly proportional to the displacement. As the displacement increases, F increases, and as displacement decreases, F decreases, such that the proportionality constant is a characteristic of the spring. He called this proportionality constant stiffness constant or spring constant. هو لقى إنه الأف مرتبطة بالإكس بكونستنت، وهيدا الكونستنت بيعتمد على السبرينج اللي نحن عم نستعمله. الأف بتكبر لأنه الإكس بتكبر، وشي طبيعي نحن لما نعمل compression أكتر بتزيد الفورس، لما نعمل elongation أكتر كمان بتزيد الفورس. So as an algebraic value F equals minus kx, and this minus sign is because F is a restoring force، يعني force بترجعنا على equilibrium position على طول. It tries to restore the natural length of the spring. Now, the restoring force or the elastic force is a conservative force. What is a conservative force? It is a force whose work does not depend on the path followed when the particle moves from an initial position to a final position. How to check if a force is conservative or not? We simply do curl F. If curl F is equal to 0, then it is conservative. Otherwise, it's not conservative. Every conservative force derives from a potential. It has its own potential. In our case, the elastic force derives from the elastic potential energy. What's the relation between F and U? The force and the energy, they are related this way. So du, an infinitesimal variation of the potential energy, equals minus dW of F, where W of F is the work done by the force F. W of F or dW of F is simply F dot dr. We substitute F by its value. F will be equal to minus kxi. We substitute dr by its value. It's dxi plus dyj plus dzk. So multiplying these two together, I with I, j with j, k with k, so we can see there's no j's and no k's, we'll end up with minus kx dx. So multiply only the first two terms. So minus dw of f is equal to kx dx. So if I put minus here, so we will get plus kx dx. This is the infinitesimal variation of the potential. To get u, the total elastic potential energy, we have to integrate. Integral kx dx, it's equal to half kx squared plus a constant, a certain constant. How to find this constant? We choose a particular point, substitute this point, find u reference. So we know that when x is equal to 0, we consider that the potential energy is equal to 0. That means when the particle is at equilibrium position, it has no elastic energy. The spring is not exerting any force on the particle, and we can assume that its elastic energy is equal to 0. So if u is equal to 0, in the case of x equal to 0, we arrive to u reference equals to 0. So we deduce u reference equal to 0, and the formula of u will appear as only half kx squared. K is the stiffness of the spring and x is the elongation of the spring. Now, if we want to plot u as function of x, we can see clearly it will be a parabola. It's function of x squared. So this is the shape of the graph of u as function of x. It's a parabola with minimum at x equals to 0. The shape of the potential curve is a parabola simply because we have started with a force F equals to minus kx. It's due to Hooke's law. So if F was a different force, then we won't arrive to the same result. Now assume we have a particle oscillating with an amplitude A. So x maximum will be equals to A. This is the maximum x. And x minimum will be equal to minus A. The particle will have energy. This energy will be equal to the potential energy when x is at the minimum or x is at the maximum value. Why? Because at the minimum and the maximum values, the kinetic energy is equal to 0 and all of the energy is potential energy. So you can see here that at the extremities, all the energy is a potential energy. Let's take another point. So, if for example, the particle is at a position, let's say x equals a over 2, so in this case, part of its energy will be kinetic and the other part will be potential, such that their sum is equal to E. So if this is the part that is potential, then this is the part that is kinetic, it's called T, such that U plus T must be equal to E. At x equals 0, at the middle, you can see that U is equal to 0 and all the energy is kinetic. لما البارتيكل تكون عم تعمل oscillation ما بين minus A و A, الانرجي تاعتها بتضل constant. This line represents the energy. It's constant. It's horizontal. البوتنشال energy عندها شكل parabolic. على الاكستريميتيز الانرجي مع البوتنشال energy they intersect. هيدا بيعني انه بهاي النقط اللي هن هون وهون والانرجي هي كلها potential. الكاينتيك is equal to 0. بكل المراحل الثانية بيكون الانرجي جزء منها كاينتيك جزء منها potential. أكيد ما عدا السبيشال كيس اللي هي بالنص بيكون عندي potential energy is equal to 0. السبرينج لا contracted لا elongated وبهذه الحالة الانرجي كلها هي kinetic. Let's find the equation of motion governing the motion of this particle while it is oscillating around the equilibrium position. So let's start with Newton's second law. Newton's law says that the summation of forces is equal to the mass times the acceleration of the particle. The only force acting on the particle is the... Now let's find the equation of motion of the particle oscillating around an equilibrium position. Using Newton's law, F equals ma, substitute for F the restoring force minus kx, we get minus kx equals ma. A is the second derivative of position, so A is equal to x double prime, it's equal to d squared x by dt squared. So as you can see, minus kx equals mx double prime, arrange you will get mx double prime plus kx equals 0. This is a second order differential equation of x. The solution of this equation is sine or cosine function, or summations of sines or cosine. So one of the solutions of this differential equation may be given as x equals a, the amplitude of the oscillation, the amplitude of x, the maximum of x, cosine, or it can be sine, 2 pi nu, with the nu being the frequency, 2 pi nu being the angular frequency, t plus phi, phi is the phase, t is the time. So this is called the time equation of motion. Time equation of motion. It gives a solution for the differential equation. So this is the differential equation. It gives x as function of t. So whenever we know t, we are able to know x. This is a time equation. You have time, you can find x at an instant. Now if we take this x and resubstitute this x in the differential equation, let's do that. So to substitute x in the differential equation, we have to calculate x double prime. To calculate x double prime, we have to calculate x prime first. So x prime is equal to a, we get out 2 pi nu, cosine becomes minus sine, so it's minus sine 2 pi nu t plus phi. This is x prime. X double prime is equal to minus a, so again 2 pi nu squared, sine becomes cosine, so cosine 2 pi nu t plus phi. If I insert x double prime in the differential equation, I will write here up, so x double prime plus kx is equal to let's substitute for x double prime, a 2 pi nu squared, cosine 2 pi nu t plus phi, plus k, whereas x is equal to a cosine 2 pi nu t plus phi equal to 0. So this equation is always true for all values of t. So let's take cosine common. Cosine is not zero. The amplitude is not zero. So we are left with minus 2 pi nu squared times m. So I forgot m here. So this is m times m plus k is equal to 0. So as you can see, we arrive to minus 4 pi squared. This is nu squared. M equals minus k. And nu, it's equal to 1 over 2 pi radical k over m. A simple arrangement will lead to that. So nu squared equals k over m times 1 over 4 pi squared implies nu equals 1 over 2 pi radical k over m. This shows that if the particle is connected to a spring, this particle has a mass m and the spring has a stiffness k, then the particle will oscillate with a frequency equal to 1 over 2 pi radical k over m. The frequency of oscillation does not depend on the energy of the particle. It only depends on the mass of the particle and on the stiffness of the spring, on m and k. Now, after studying the vibration of a single particle connected to a spring, understanding its elastic potential energy and its equation of motion, it's the time to study the vibration of two particles connected with a spring. Let's consider two particles, M1 and M2, connected with a spring of a stiffness K. Let's call X1 and X2 the displacements of the particles M1 and M2 from their equilibrium positions. Assume these are the two particles and this is the natural length of the spring. This is L0, this is the equilibrium position 1 and this is the equilibrium position 2. So this is M2. Assume that when it's oscillating, for example, M2 will be displaced by a distance x2. So this is x2, M2 will be here. And assume that M1 will be displaced by a distance x1. x1 and x2 are not necessarily equal. They are just displacement for each one from its equilibrium position. So in this case, the elongation of the spring is equal to x2 minus x1. So delta L of the spring is equal to x2 minus x1. ليه؟ لأنه هو طول من هون x2 وقصر من هون x1 فإن total بيكون طول x2 minus x1. You can understand it this way. Similarly, if the particle has moved to the left, particle 1 has moved to the left, so this is M1 and this is M2. If they have moved in opposite directions, for example, and also we have elongation of the spring, so you can see that in this case x2 is positive while x1 is negative. So x2 minus x1 is simply absolute x2 plus absolute x1 لأنه x1 is negative. هون بهيدا الإكزامبل الثاني هو طول من هاي الجهة x2 وطول من هيدي الجهة x1 absolute value x1. So total elongation will be absolute x2 plus absolute x1. I'm just allowing you to see that x2 minus x1 covers all the values for all the cases of the spring and it gives me the elongation of the spring or the compression of the spring for all values of x1 and x2. So we deduce that delta L equals x2 minus x1 for all positive or negative values of x1 and x2. Now the kinetic and the potential energy of the system formed of the two particles is the kinetic energy is equal to the kinetic energy of the first particle plus the kinetic energy of the second particle. It's half m1 v1 squared. v1 is simply x prime 1 and half m2 v2 squared is simply half m2 x2 prime squared. U is the potential energy. It's equal to half k delta L squared. It's simply x2 minus x1 squared. So we have only one spring, one elastic energy. Now we have our equations. Now our equations depend on two variables, x1 and x2. In order to find the equation of motion, we can either use Newton's laws or we can use the Lagrange equation. To use the Lagrange equation, we may write d over dt del t over del xi prime plus del u over del xi is equal to 0, where xi is simply once بنجربها على x1 and the other time we try it for x2. So we have two equations. Two equations, it means we have the kinetic and potential energies of the system formed of the two particles are given by, so the kinetic energy is equal to the summation of the kinetic energy of the first particle plus the kinetic energy of the second particle. It's half mv1 squared, m1 v1 squared, plus half m2 v2 squared, where v1 is simply x1 prime and v2 is x2 prime. Now the elastic energy of the system is equal to half k delta L squared, where delta L is the elongation or compression of the spring, and delta L is equal to x2 minus x1. There's only one spring, so one elastic energy. Now you can see that our kinetic energy and potential energy depend on two coordinates, x1 and x2. So in order to find differential equations that govern these two coordinates, x1 and x2, we are going to use the Lagrange equation. The Lagrange equation is given by d over dt del t over del xi prime plus del u over del xi equals to 0. Because we have two particles, 1 and 2, the Lagrange equation for particle 1, for I equals 1, the Lagrange equation will be d over dt del t over del x1 prime plus del u over del x1 equals to 0. So if we go to the kinetic energy and we do a derivative with respect to x1 prime, you can see that the second term, half m2 x2 prime squared, will be cancelled and we get d over dt half m1 2 x1 prime plus the derivative of u with respect to x1 will be half k, so we do a derivative 2 minus 1 and we get x2 minus x1 equals to 0. Now let's do a derivative of time for the first term. These two are cancelled, we get m1 x1 double prime. These two are cancelled, so it's minus k x2 minus x1 equals to 0. So once we do the derivative with respect to x1 and the other time we do it with respect to x2, we will get two equations with two unknowns that are our parameters and try to find the solution of these two parameters. So if we do the Lagrange equation for x1, we will get d over dt del t over del x1 prime plus del u over del x1 equals to 0. So let's take the time. Same for particle 2. For I equals 2, d over dt, the partial derivative of the kinetic energy with respect to x2 prime plus the partial derivative of the potential energy with respect to x2 is equal to 0. So it will give me the derivative with respect to time of the partial derivative of t with respect to x2 prime is simply half m2 to x2 prime, and the partial derivative of u with respect to x2, it is 2 x2 minus x1. This is equal to 0. So half with 2 is cancelled. Here half with 2 are cancelled. The derivative of x2 prime with respect to time is x2 double prime. So we get m2 x2 double prime plus k x2 minus x1 equals to 0. It's the same equation as this one. So now using Lagrange equation, we were able to arrive to two equations containing the coordinates x1 and x2. x1 and x2 are our unknowns. We are searching for their values or their solutions. By the way, these two equations can also be found using Newton's laws. How? Let me tell you how. So for particle 1, the force is equal to ma. The elastic force is equal to mass times acceleration. So let's say m1, a1. The elastic force is equal to minus k x1 minus x2, because the elongation of the spring is expressed as x1 minus x2, the difference between the two coordinates. It's equal to m1 x1 double prime. And this equation is the same as this one. So this is particle 1. For particle 2, the same, F equals m2a2, but the force here it's minus k x2 minus x1. It's equal to m2 x2 double prime. And this equation here is the same as this equation. Remember that in the simple case where we had only one spring, one particle, the equation was minus kx equals mx double prime. But here we had to do x minus x because we have elongation or compression from both sides of the spring. Remember that we are searching for the solutions of the coordinates x1 and x2 as function of time. A first guess would be taking x1 and x2 in a way similar to that for a single particle. So for a single particle, the solution was x equals a cosine 2 pi nu t plus phi. So let's try to take x1 equals a1 cosine 2 pi nu t plus phi for the first particle, and x2 equals a2 cosine 2 pi nu t plus phi for the second particle. It's obvious that we did not put equal values for the amplitudes in x1 and x2 because there's no necessity that the amplitudes are equal, but the frequency in both equations is the same because it's the same spring, it's the same oscillation, so it must be the same frequency. So using these expressions for x1 and x2 and trying to put them in the previous differential equations that we have found using Lagrange equation, first we have to calculate the second derivatives. So I've done this before. Calculating the second derivatives will give us minus 4 pi squared nu squared a1 cosine 2 pi nu t plus phi. And similarly for x2 w prime, I will take these solutions with x1 and x2 and insert them in the differential equation of the previous slide. So here I'm going to insert x1 double prime, insert x2 double prime, x1, x2 double prime, x2, and x1. So you will see that we will get, if I insert here, I will get m1 minus 4 pi squared nu squared a1 cosine 2 pi nu t plus phi minus k a2 cosine 2 pi nu t plus phi minus a1 cosine 2 pi nu t plus phi. All of this is equal to 0. Get rid of the cosine term. It's not equal to 0 for all time. So we are left with m1 minus 4 pi squared nu squared a1 minus k a2 minus or plus k a1, because minus k is multiplied by minus k is multiplied by minus a1. It's equal to 0. Let's arrange a1 together. So we will get minus 4 pi squared nu squared m1 plus k, all of it multiplied by a1 minus k a2 equals to 0. And we get a first equation that contains the amplitudes a1 and a2 together. We will do the same for the second one. You can do it yourselves, and you will get a second equation containing the amplitudes a1 and a2. Okay, so here it is. It's minus 4 pi squared nu squared m1 plus k a1 minus k a2. Similarly, we insert in the second differential equation and we arrive to this equation which joins a1 and a2, which are the amplitudes of oscillations. So, non-trivial solutions for a1 and a2. a1 and a2 exist. there are amplitudes for oscillations if they satisfy these two equations at the same time. And this is true if the determinant is equal to 0. This determinant, so we arrange it. This the first coefficient multiplied by a1, the second coefficient, this is the first coefficient multiplied by a1, the second coefficient multiplied by a2, the first coefficient multiplied by a1, the second coefficient multiplied by a2. So we arrange them. Solutions for a1 and a2 exist other than a1 0 and a2 0, because these solutions are not accepted, because if a1 is 0 and a2 is 0, it means that there is no oscillation. So non-trivial solutions exist if the determinant is equal to 0. So let's try to search what this determinant gives us if it is equal to 0. This is a, b, c, d, a times d minus c times b. So a times d minus c times b. So this is the determinant. We will arrive to this. This is the term. So we will get minus 4 pi squared mu squared m1 plus k multiplied with minus 4 pi squared mu squared m2 plus k minus k, this will be k squared. So if we try to expand this, we will get 4 pi squared mu squared m1 m2 all over squared for sure, m1 m2. This is, I've multiplied this by this. Now multiplying by this with this will give us minus 4 pi squared mu squared m1k minus 4 pi squared mu squared m2k. So I'm doing this with this. And at last we have plus k squared minus k squared. So you can see that we have arrived to the same equation as here, but here he took m1 plus m2 common, so we arrived to the same equation. K squared minus k squared cancelled, so we are left with an easy equation. Let me erase ink. So now these two are cancelled, and now it's easily solved. Let's take 4 pi squared mu squared common. So we are left with 4 pi squared mu squared m1 m2. So this is a new m1 m2 minus k m1 plus m2. This must be equal to 0. For sure, we have two solutions. Either this term is equal to 0, which means that nu is equal to 0. So this gives us nu equals to 0. Either this term is equal to 0, which gives us nu squared equals k m1 plus m2 over 4 pi squared m1 times m2. But we already know that m1 times m2 over m1 plus m2 is the reduced mass of a system of two particles. So mu squared can be written as k over 4 pi squared mu. And mu will be equal to 1 over 2 pi radical k over mu. So we arrive to this formula. So nu has two solutions. Either nu can be 0, or mu is equal to 1 over 2 pi radical k over mu, where mu is the reduced mass of the system of particles. To understand the meaning of these two frequencies, let's insert their values in the equations of A1 and A2 and see the relation between A1 and A2. For nu equals 0, I'll use the first equation. You can use any one of them. So we have minus 4 pi squared mu squared m1 plus k, this is multiplied by a1 minus k a2 equals 0. So this is the first equation of a1 and a2. I'm going to substitute nu equals to 0. So this term will be equal to 0. We will get k a1 minus k a2 is equal to 0, and a1 is equal to a2. So a1 cosine 2 pi mu t plus phi, it's equal to a2 cosine 2 pi ut plus phi, we end up by x1 equals x2. This means that if particle A undergoes a displacement x, then particle 2 undergoes the same displacement in the same direction. This is a translational motion of the entire system. It's all moving together. Now let's try to substitute nu equals 1 over 2 pi radical k over mu. So this will be minus 4 pi squared, and mu squared is 1 over 4 pi squared k over mu multiplied by m1 plus k a1 minus k a2 equals to 0. For sure k, we can get rid of it. It's everywhere. And minus 4 pi squared, we are left with mu is equal to m1, m2, so we're left minus, this is m1, m2, m1 plus m2. I've substituted for mu m1 plus 1 a1 minus a2 is equal to 0. So here m1 with m1 is cancelled. We are left with m2 down. So this is m2 here. Sorry for my handwriting. But this fraction here appears to be like this. It's minus m1 minus m2. I'm going to add the 1, so it will be plus m2 over m2. So I've made them a single fraction. a1 minus a2 is equal to 0. So m2 with m2 cancelled. We are left with minus m1 over m2 a1 minus a2 is equal to 0. It's minus m1 over m2 a1 equals a2. So if I want to write it as a fraction of a1 over a2, it's equal to minus m2 over m1. So this is the relation that we have arrived to, similar to the one given here in the slide. If we multiply up with cosine 2 pi nu t plus phi and down the same value, so we will arrive to x1 over x2 equals minus m2 over m1. For this frequency of oscillation, we can observe that the displacement x1 and x2 depend on the masses m1 and m2. So if the masses m1 and m2 are equal, then in this case x1 will be equals to minus x2. So both particles will move in opposite directions with the same amounts. But if the masses are not equal, let's say for example one of them is larger than the other, then the one with the lighter weight will move with a greater amplitude than the heavier one. So let's take an example. Let's assume, for example, M1 is greater than M2. So it's much greater than M2. M1 is the heavy one, and M2 is the light one. The ratio M2 over M1 is very small. Then x1 over x2 is very small, which means that x1 is much smaller than x2. So the displacement of 1, which is the heavy one, is much less than the displacement of 2, which is the light one. One last note, the frequency of oscillation, nu, is equal to 1 over 2 pi radical k over mu, where mu is the reduced mass of the system of particles. If we compare it with the frequency of a single particle, is equal to 1 over 2 pi radical k over m, we can see that we only replaced m with a mu. We deduce that for two particles connected by a spring, they can be represented by an equivalent simple mechanical model, that is a material point that has a mass equal to the reduced mass of the system of particles. So بدون ما ناخد السيستم كله كاتنين particles and study it in details فيها نعتبره إنه هو particle وحدة عندها mass mu. This is a second method to study the vibration of two particles connected by a spring. All you are going to do is replace our coordinates x1 and x2 with the new coordinates q and x. Let's introduce q, which is equal to x2 minus x1. Remember, q is the elongation of the spring or the compression of the spring. And x equals m1 x1 plus m2 x2 over m1 plus m2. So it can be written like this, m1 x1 plus m2 x2 over m1 plus m2, where x, as it appears from its definition, is the displacement of the center of mass of the system from its equilibrium position. هلأ شو الهدف من استعمال coordinates جداد Q و capital X؟ هيدول الكوردينتس إذا أنا بستعملهم بلاجرانج equation رح يطلع عندي اثنين equations independent من بعض، وحدة in terms of Q وحدة in terms of capital X، مش مثل ما صار معنا المرة الماضية نفس equations طلع فيهم x1 و x2. So it will give me an easier way to treat the same problem. هلأ how to deal with this؟ أول شغلة لازم نعملها لحتى نقدر نحن نستخدم لاجرانج لحتى نوصل للديفرنشال equations. We have to write the kinetic energy والpotential energy in terms of Q and capital X. بس نكتبهم in terms of Q and capital X we are able to do the partial derivatives. بعد ما نعمل partial derivatives we arrive to our equations. So first we are going to write x1 and x2 in terms of capital X and Q so that we are able to insert x1 and x2 in the equations of kinetic energy and in the equation of potential energy. To find the first equation, let's write x2 equals, using this equation, q plus x1. And then I'm going to insert x2 in the second equation. So I will get, I write it here, x equals m1 x1 plus m2 q plus x1. I'm trying to get rid of x2 and keep only x1 to find x1 over m1 plus m2. Implies cross multiply m1 plus m2 x, it's equal to m1 plus m2 x1 plus m2 q. m1 plus m2 x1 it's equal to m1 plus m2 x minus m2 q. Divide by m1 plus m2, so x1 is equal to x minus m2 over m1 plus m2 q. So we arrive to this equation. So similarly for the second one, you can do it on your own. We can find x2 in terms of capital X and Q. So once we find x1 and x2, now we can insert them in the equation of kinetic energy. So let's insert them here and here. So we will get half m1 x prime minus m2 over m1 plus m2 q prime, all of it squared, plus half m2 x prime plus m2 over m1 plus m2 q prime, all of it squared. So it's simply half, there's no enough space, let me write here. So it's half m1 x prime squared plus m2 over m1 plus m2 q prime, all of it squared. This is here, this is all of it squared minus 2 m2 over m1 plus m2 x prime q prime. So this is the first term. The second term is half m2 x prime squared plus m1 over m1 plus m2 q prime, all of it squared, plus 2 m1 over m1 plus m2 x prime q prime. So you can see that we have this term is multiplied by half m2, and here this term is multiplied by half m1, so they will be similar and they will cancel. So this term will cancel up with this term. It will be m1 m2 over m1 plus m2 x prime q prime. We are left with half m1 x prime squared plus half m2 x prime squared, and we are left with plus half m1 m2 squared over m1 plus m2 q prime squared plus half, and this term is m2 m1 squared, this is all of it squared, over m1 plus m2 all of it squared q prime squared. So as you can see, we arrive to half m1 plus m2 x prime squared plus half. Let's take as common m1 m2 q prime squared over m1 plus m2 squared. So we are left with m1 plus m2. m1 with m2 is cancelled, so we are left with half m1 m2 over m1 plus m2 q prime squared. As you can see, this is the form. Now for the potential energy, x2 minus x1 is half kq squared, where x2 minus x1 is easily q. So now we have written t and u in terms of the new coordinates x and q. We are able to use Lagrange equation. So do your derivative and you will arrive to mu q w prime plus kq equals 0. This is the first equation. And m1 plus m2 x w prime equals 0. This is the second equation. So the first equation, mu q w prime plus kq equals 0, is the same as that of a simple harmonic oscillator with mass mu. This is the reduced mass of the system of particles, and which gives us a frequency nu equals 1 over 2 pi radical k over mu, with a solution q equals a cosine 2 pi nu t plus phi, where nu is the frequency of vibrations, q is the coordinate x2 minus x1, and a is its amplitude. Now for the coordinate x, we can see that m1 plus m2 x double prime is equal to 0, which means the second derivative of x is 0 and the x prime is constant. So the speed of the center of mass is constant. This means that this differential equation shows that a possible solution is that the system of particles may be in a translational motion. So, two possible solutions. One of them is that our system is oscillating with a frequency nu equal 1 over 2 pi radical k over mu. K is the stiffness of the spring, mu is the reduced mass of the system, or our system is translating all together. When a system oscillates with a frequency mu equals 1 over 2 pi radical k over mu, its potential energy U equals half k x2 minus x1 squared is equal to half k q squared. We can replace k by its value. It's equal to nu squared equals 1 over 4 pi squared k over mu. So we will get k equals 4 pi squared mu squared. So in this case, u is equal to half 4 pi nu squared mu q squared. So this is the potential energy. You can see that the potential energy in the case of a harmonic oscillator is a parabola and has a minimum at Q equals 0. Now, what about the vibration of diatomic molecules? We have up till now considered a potential energy that is parabolic, but the real potential energy of diatomic molecules is not a parabola. So, a typical potential energy curve of a diatomic molecule is shown in the adjacent figure. You can see its shape. This is the potential energy curve of a diatomic molecule, and this is the parabola. As a first approximation, we are interested in small displacement of the atoms from their equilibrium position or small distortions of the bond from its equilibrium length. So let's expand the potential energy around its minimum value Q equals 0 using Taylor series. So the potential energy of Q equals the potential at 0, we are expanding at 0, the derivative at 0 times Q plus half the second derivative of U at 0 times Q squared, etc. So the potential at 0 is equal to 0 because 0 is the equilibrium position and the energy at the equilibrium position is 0. The first derivative is also equal to 0 because at the equilibrium it is a minimum and the first derivative will be equal to 0. For small displacement or small distortions of the bond from its equilibrium value, we can approximate U, the potential energy of a diatomic molecule, to half second derivative of U at 0 times Q squared. You can see that it's proportional to Q squared. It's similar to that of a harmonic oscillator. So for small distortions, we can assume that the potential energy curve of a diatomic molecule is approximately the same as a parabola. So in regions close to Re, equilibrium bond length, the potential energy can be approximated by a parabola, so we can write U equals half Q kq squared, where k is the force constant of the bond. K is the second derivative of the potential energy with respect to Q. And Q is equal to, as we have seen, is x2 minus x1 or R minus Re, because x2 minus x1 is simply the elongation of the spring, and in our case, it's the elongation of the bond, it's R minus Re. R is the length of the bond, Re is the equilibrium length of the bond. If we are going to use this approximation that the potential energy at small distortions is equal to half kx squared, so we're going to treat our oscillator as a harmonic oscillator. Now we are going to treat the vibrations of a diatomic molecule quantum mechanically. To do that, we're going to write the total energy of a diatomic molecule and its corresponding Hamiltonian to be able to find its eigenvalues and eigenvectors. The total energy of the diatomic molecule is the sum of its kinetic energy and potential energy. The kinetic energy is due to the two atoms, the first atom and the second atom. So P1 squared over 2m1 is due to the first atom, P2 squared over 2m2 is due to the second atom. These two can be replaced by this term. This term was proved in a previous slide. So the first part of this term corresponds to the translational motion of the center of mass. It's half the total mass of the system, multiplied by V of the center of mass squared. And the second part is due to the vibration or oscillation around the center of mass, oscillation of the atoms around the center of mass. It's equal to half mu, which is the reduced mass, q prime squared, which is related to the oscillation of particles. In reality, the second method is quite good because it separates two different motions from each other, the motion of the center of mass and the oscillation around the center of mass. So if we want to write the Hamiltonian, we may write the Hamiltonian in this way. And by this, we are able to separate the relative motion of the atoms from the motion of the molecule as a whole. So what we have done here is that we have replaced half m1 plus m2 x prime squared with minus h bar squared over 2 m1 m2 nabla squared of the center of mass. This represents the kinetic energy of translation of the center of mass. And the second one is due to the oscillation motion around the center of mass. So you can see there is mu, so as if we have a single particle of mass mu. Plus U is the potential energy. So we are left with this Schrodinger equation. If we are going to neglect the translational motion of the center of mass because we only care for the vibrational motion around the center of mass. So our Schrodinger equation will be minus h bar squared over 2 mu nabla squared psi plus half kq squared psi is equal to E psi. We have substituted u for half kq squared because, as we have said, we are going to consider a harmonic oscillator. The solution of this differential equation is not developed here in this course, but this equation is a standard equation in the theory of differential equations and its solutions are well known. The quantization of energy or the quantization of the eigenvalues E arise from the boundary conditions. The boundary condition states that psi must tend to 0 when Q tends to plus or minus infinity, which is logical. So for an infinite stretching or infinite compression, the probability must tend to 0, so psi must tend to 0 if Q tends to plus or minus infinity. Anyway, we're not going to deal with the solution. The eigenvalues or the permitted vibrational energy levels were found to be E nu is equal to h bar omega nu plus half equals h nu nu plus half. Please pay attention, there are two symbols for nu. This one represents the vibrational frequency of the bond, the vibrational frequency of oscillations. And this one is a quantum number. It can take the values 0, 1, 2, etc. Omega is the angular frequency of vibration. H is Planck's constant. H bar is equal to h over 2 pi, and for sure omega equals 2 pi nu.